Well, hello, chemistry class. I am so sorry that we're not able to get together today, but I thought I would do a recording from the PowerPoint lectures, and you guys can just kind of watch through this, and maybe this will be helpful to you. The plan this week is for you to work on Chapter 2. Besides working through Chapter 2 over this week, I will also include the chapter test for you guys that you can take later on, either in the week or on Monday of next week. And then we'll come in and talk about Chapter 3 next week. So if this all goes well, this will be our way of working through Chapter 2. I am sad about not being able to see you in person, and it does take away some of the fun of the experiments and stuff like that. But at least we can get through the main parts of the material here. There's not a lot of experiment kind of things I'm going to do with Chapter 2 anyway, so this kind of works out. Hope you guys are staying dry and safe, and we're going to jump right into this together. So section 2A is on the classification of matter. So what is matter? Well, you guys already have a definition for this, so let's see if you can remember. What is matter? How do you define matter? Have you said it already? Have you said it out loud? All right, so matter is operationally described as anything that occupies space and has mass. Remember, we said that the chemistry is the study of stuff, or the study of matter, and the changes it undergoes. Matter is anything that has mass and volume. Anything that has mass and takes up space. Matter was created ex nihilo, out of nothing by God. So that's a Latin phrase, just means that God made everything out of nothing. Now, the idea of classifying matter can travel us all the way back to the accounts in the book of Genesis, where Adam and Eve are created. We know that Adam in particular was given the task of classifying all of the animals. Each of the animals was brought before him, and he was supposed to name each one. And I think among the reasons that God has Adam do this is he recognizes by the end of all of that classifying that not one of the animals was like him. And it's almost as if God is setting Adam up for recognizing his need for a helpmate, one that was made as a suitable companion for Adam. And so we know after Adam names all these animals and none of them are like him, God causes Adam to go into a deep sleep. He takes from the man's side. He fashions that into a woman. And when Adam sees Eve, he says, "Oh, now this is bone of my bones and flesh of my flesh." But just understand that like kind of zoological idea of like classifying animals and giving names to things, like this is part of what it means for us to exercise a wise dominion over the earth. So what we're doing here in this chapter is just wanted to classify everything. That means all of matter, all of the stuff of the universe. How do we go about putting together a classification scheme for all of that? So in order to do that, before I can talk about how all of matter is kind of grouped and divided into various categories, we need to begin by talking about the properties of matter. So properties are the distinguishing characteristics of matter. The characteristics can be divided into two main classes. There are those characteristics that are physical in nature and those which are chemical in nature. So we have physical and chemical characteristics of all of matter, or properties of matter. A physical property is any property that can be observed or measured without altering a substance's chemical composition. And I'm going to give you some examples of that. The chemical property is any property that describes the way that matter acts in the presence of other materials, or the way that it changes composition under certain conditions. Now, the big thing you're going to keep track of both physical and chemical properties is this idea of if something happens to the actual substance as a result of being in the presence of something else or under certain conditions, that is a chemical property. Otherwise, it is a physical property. And again, we'll give you some examples. But before I do, let's just talk about physical change and chemical change. So a physical change is any change in the appearance or shape or state of matter of a material that does not cause a change in its chemical composition. So any change in appearance, any change in shape, or the state of matter that doesn't change its chemical composition. So here we have a picture of like boiling liquid, and I guess assumingly boiling water. So if water is boiling, it's turning into vapor. That's a change of state, right? It's the state of matter is going from liquid to gas. but it is still water. And for that reason, this is not a chemical change when you boil water. It's just a physical change. You're changing it from liquid state to gaseous state. Now, a chemical change is any change that causes a substance to change its chemical identity, also known as a chemical reaction. We have a picture here of a rusted bolt, right? So the idea here is that orangey kind of shade on the outside of the iron there, we know as rust. And rust is just iron oxide. So oxygen has combined with iron to form this new chemical substance called rust or iron oxide. And that's a chemical change. So physical properties are things like this: color, shape, texture, the state of matter. That's if it's liquid, solid, or gas. Those are the three main ones. We'll talk about some more in a minute. The odor, how it smells, how it tastes, the density, the malleability, ductility, and conductivity. So let me talk about each of these real quick. So color and shape and texture, those all make sense, right? The state of matter I just explained, is it liquid, solid, or gas? Odor, taste. Okay. So density, let's talk about these last four. So density is just the measurement of the amount of mass in a certain amount of volume. So it's a measurement of how much stuff is packed into how much space. How much stuff is packed into how much space. So how much mass into how much volume. And so the formula that we'll normally see when it comes to densities, you'll see something looks like this: density equals mass divided by volume. So mass is measured in grams or kilograms, and volume in cubic centimeters or milliliters, that kind of idea. But it's always a mass over volume is density. So it's how much stuff is packed into how much space. So again, if it's more dense, then there's more stuff packed into the same amount of space, or we have the same amount of stuff packed into less space, right? That kind of idea. Either way works. More dense means that there's more stuff per unit of volume. Now, malleability is the ability to hammer something into thin sheets, like to press it out. We usually think about this with metals. Probably the most famous example of this is gold. Gold is exceedingly malleable. You can take a small amount of gold and you can press it out very, 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 very thin, and it can be then overlaid on all kinds of things. We see examples of this even in the Old Testament with some of the objects that were used in the worship of Israel. They would build things and they would overlay them with gold, for example. And gold does really well as an overlaying because it can be pressed out into very, very thin sheets, and it can make a lot of things look like gold if you just lay them over them. So that's malleability, being able to hammer it out into sheets. Ductility is the ability to take a metal to draw it into a thin wire. So ductility is drawing out something, taking a piece of something and being able to draw it out. Think of, like, for example, like taffy. When they take taffy and they pull it out and they can stretch it and it kind of becomes a thin line in between as they pull it out. Ductility is this property of being able to draw something into a wire. Conductivity can be both regarding heat conductivity as well as electrical conductivity. So you can measure how a substance will conduct heat and how a substance can conduct electricity. Now again, all of these properties we've just talked about are all physical properties. Now, as far as chemical properties, there's really three main categories of chemical properties. There is reactivity, so that's how this substance behaves under the presence or in the presence of another substance. There is flammability, which has to do with the substance's ability to burn in the presence of oxygen. And then there is toxicity, and that is how the substance it behaves within the human body or within living organisms. So usually those three chemical properties are the ones that we talk about: reactivity, flammability, and toxicity. And if I was to show you guys, for example, a sample of some sort of chemical reagent that we had in the lab, oftentimes there will be a warning label on the side of the bottle that will talk about those three things: reactivity, flammability, and toxicity. And they'll give you kind of an indication of how strong that chemical is as it relates to being reactive, as it relates to being flammable, as it relates to being toxic. So those three properties are the big ones when it comes to chemical properties. Okay, now having established both physical and chemical properties, we can now talk for a minute about the way in which we take all of matter and subdivide it into groups. And the main division is regarding pure substances and mixtures. Scientists use chemical and physical properties to organize matter into both pure and mixtures. So pure substances or mixtures. So you kind of have a flow chart. At the very top would be matter, which is everything, right? All the stuff. And underneath that would be two categories, pure substances and mixtures. Now, a pure substance is any material that consists of only one type of matter, an element or a compound. So when we say a pure substance, it can be either an element or a compound. An element is like from the periodic table, right? It could be carbon or oxygen, that kind of idea. A compound is like when we have things that are chemically joined together. For example, table salt, which is sodium chloride, NaCl. That would also be a pure substance because it's just the salt. So it can be a combination of elements that have been joined together in a chemical bond, or it can be just the element by itself. Either way, those are called pure substances. A mixture is a combination of two or more substances that are physically combined in a changeable ratio. So you could have, for example, like the air that we're breathing right now, right? That is a mixture. It's a combination of several gases made up primarily of what? What gas is mainly in the air? Somebody know? It is nitrogen. Nitrogen makes up about 78% of the air that we breathe. And then does anybody know the next most prevalent gas in the air that we breathe? Yes, it would be oxygen. I know you were saying that, right? And it's something around 21% oxygen. And then what's left, like the 1% that's left, is made up of mostly carbon dioxide, but then there's like other trace gases, some noble gases like helium and stuff of that nature. Water vapor, stuff of that. All right, so then you have what are called heterogeneous mixtures as well as homogeneous mixtures. So a heterogeneous mixture is a mixture in which you can still see the separated parts. Homogeneous is when it's been mixed together thoroughly and you can't tell the difference between them. Heterogeneous mixtures, like a good example, like on a big scale, would be like if you're looking at Jell-O that had like fruit in it, right? Or you were eating a chocolate chip cookie. The cookie dough itself is probably homogeneous, but the chocolate chips are kind of like that picture of heterogeneous, where the way you can tell if a mixture is heterogeneous is if you took a sample from it and then took a sample from somewhere else, it's possible that you get different percentages of stuff in those two samples. If it's homogeneous, no matter where you take a sample from the mixture, it's always going to give you the same percentages of things. That would mean it's homogeneous. So here's kind of a good, these are formal definitions. A heterogeneous mixture is a mixture that has two or more distinct regions, which give it a non-uniform appearance, whereas an homogeneous mixture is a mixture that has only one phase, which gives it a uniform appearance. So homogeneous mixtures, one phase giving a uniform appearance. Heterogeneous, two phases, non-uniform. So technically, even in the air that I'm breathing, like the air itself might be homogeneous, but there might be, like, for example, dust particles, like little solid particles that are floating around. Now, those little particles would be not part of the homogeneous mixture, which is air. So that would make it a heterogeneous mixture because I have air, which would be homogeneous, but the dust particles that are floating around in it would make it heterogeneous. So just to give you an example, heterogeneous, you have things that are like, a non-uniform appearance, two or more distinct regions. Homogeneous is when everything's in one phase and has a uniform appearance. So if you want to separate a mixture, there are a couple of different ways that you can do that. Since mixtures are combined physically, they can be separated by physical means. The method of separation depends on the physical properties of the substances that are involved. Now, the methods of separation, here's the major ways in which we can separate things. So the first is filtration. Filtration is a process of separating mixtures on the basis of particle size. And I'm sure that we've all done this on some level. If you've even made macaroni and cheese lately, and after you've boiled the water and put the pasta in there, or any other pasta for that matter, when you go to pour out the water, you might put that through a strainer, right? and it allows the water to go through, but so the holes are big enough for that, but the holes are small enough that it catches all the pasta, and you keep the pasta in that, and then you pour it back into the bowl that you were cooking in, or the pot you were cooking in. So filtration works like that, and you can do it with very, very thin paper filters. For example, a coffee maker, at least the old school ones before all the Keurigs and stuff, you had this like little paper filter that you put in the top. You put your coffee grounds in there, and the water would mix with the coffee grounds, but then the water would travel through the paper, but the paper would hold back the grounds. So that's filtration. Distillation is a process where you separate a mixture on the basis of different boiling points of its components. Probably for us here down in Houston, one of the most famous examples of that is what happens in distillation towers when they're taking crude oil and they're heating it up, and then they condense it at different levels along the tower where they draw off the oil at different temperatures, because then they get different forms of use out of the crude oil. So you might get propane, you might get some gasoline, you might get some kerosene, or some again, there's various levels of which you can draw off from that. And at the very bottom, you might have the really, really thick stuff that might be used in producing rubber or plastics and other stuff of that nature. Now, decanting, it would be like, I guess, that's synthetic rubber. Decanting is a process for separating mixtures in which a less dense medium is poured off the top of a more dense medium. So if we had, for example, a mixture of oil and water, we could allow for them to separate and then pour off the top, let the oil come to the top, and then pour that off carefully until we've gotten pretty much just the oil off, and then leave behind the water. So that's decanting. And you can do that whenever there's different densities of mixtures. You can just pour off one and keep the more dense in the one jar and pour off the less dense. Okay, so having done all of that, we can now organize matter. So here's a little chart for us to kind of follow. So we have matter. It can then be split into mixtures and pure substances. The mixtures are made up of heterogeneous mixtures and homogeneous mixtures, right? Heterogeneous is the one that has like the chocolate chip cookie or the fruit inside of the Jell-O. Homogeneous is kind of like air, right? On the pure substances side, we have either elements or compounds. And through a chemical change, you can bring elements together to form compounds. But the compounds then, when just considering compound by itself, is also considered a pure substance. So we have mixtures, which split into heterogeneous and homogeneous mixtures, and then we have pure substances, which can either be elements or chemically combined elements into compounds. Now, an element is a pure substance that consists of only one kind of atom. Pure substance that consists of only one kind of atom. What is an atom? Well, we kind of already set this up a little bit, but an atom is the smallest particle that makes up an element and is capable of chemical interactions. So an atom is the smallest particle that makes up an element and is capable of chemical interactions. It comes from the Greek word atomos, meaning not, and tomos meaning to cut or cuttable, so being not cuttable. So the idea was that this is the smallest particle, and you couldn't get any smaller than that. Now, we know today that that's not true. There are subatomic particles. We'll be talking about those in this class. We'll be talking about electrons and protons and neutrons and all those interactions. But whenever we're talking about electrons, protons, and neutrons, what is still the case with an atom is that this is the smallest amount of an element where it's still the same element. So this is the smallest particle that makes up an element. If you take away the electrons, if you take away the protons, take away the neutrons, like, you no longer have the atom. So like the atom is the smallest thing where it's still that element. Okay, so the parts of the atom, as I just mentioned quickly, so in the nucleus, which is that dense, very, very, very ultra-dense core of an atom, is an extremely small, dense center that contains the protons and neutrons. So the protons and neutrons are at the very center. It's a very, very dense and very, very small center of the atom, and it's surrounded by an electron cloud. The proton is a positively charged subatomic particle. The neutron is an uncharged or a neutral subatomic particle. And then the electron is a negatively charged subatomic particle. And those are the ones that are outside. They're in the electron cloud outside of the nucleus. So let's also mention then what happens with an ion. So when the number of protons and electrons in an atom are equal, the atom is electrically neutral. But what happens if we have a different number of protons and electrons? So when the number of protons and electrons are out of balance, the atom has a net electrical charge, and it is called an ion. So an ion is whenever an atom has a net electrical charge because it has a different number of protons than it does electrons. An ion is just a charged atom or group of atoms due to the gain or loss of electrons. Note here it says due to the gain or loss of electrons. It's not saying here gain or loss of protons. The reason why is because the number of protons within the nucleus, if we were just to symbolize them as pluses here, let's say that we had 2 electrons on the outside, so we're looking at helium. If you change the number of protons inside the nucleus, you actually come to a different element. So if we were to add another proton in here, it's no longer helium. If we were to take away 2 protons, for example, and be left with 1, it's no longer helium, it's now hydrogen. So if we add or subtract electrons, it can still be the same element because the element is defined by the number of protons that are in the nucleus. So if we get ions, it's because of either gaining or losing electrons. But that does cause an imbalance. So there's more electrons than protons or fewer electrons than protons. So as far as elements go, you can have monatomic elements, which is just an element that naturally occurs as an individual atom. There are diatomic elements where the same element naturally occurs as 2 molecules or 2 atoms joined together in 1 molecule. And then you have polyatomic elements where it occurs as molecules of 2 or more atoms. So technically, anything that even has 2 is also polyatomic, but we often just call those diatomics. So a monatomic element, for example, would be like iron. So Fe would just be a monatomic element. Diatomic element would be something like oxygen, O2, H2, N2. So a lot of the gases are diatomics. Hydrogen, nitrogen, oxygen, and then fluorine, chlorine, bromine, iodine. All 7 of those are diatomic elements. So they combine with themselves. And we'll learn more together in the class why they do that. And so then these are also considered polyatomic elements, but if they have even more than that, they can also be polyatomic. Now, elements are named after many things. They can be named because of a color, or because of people that discovered them, or places where they were found, or even heavenly bodies. So there's a lot of different reasons for which the elements got their names. Sometimes even miscellaneous words. Now, the elements are named by a chemical symbol, which is either a 1 or 2-letter symbol that identifies an element. We always start with a capital letter, and then if there's a second letter, it's always lowercase. So the first letter of the name or element often serves as its symbol. Example would be hydrogen, or N for nitrogen, or O for oxygen. But if more than one element has the same first letter, then we use a second letter, and it is lowercase. So like Ca for calcium, or Co for cobalt, right? Because capital C is already used for which element? Do you guys know? Capital C is used for carbon. So since carbon already has C, then if we get to calcium, we need to just say Ca, and for cobalt, we say Co. So the subscript number indicates the number of atoms of that element that are present. Examples would be like this. I just said before N2, for example, or O2, or H2. So that just means that there's 2 nitrogen atoms there in N2. Look at O3. O3, there's 3 atoms of oxygen. By the way, anybody know what O3 is? So we think of O2, that's normal oxygen that we breathe, but does anybody know what O3 is? O3 is ozone. O3 is ozone. Now, a coefficient is the number that's in front of a formula that tells us how many molecules or atoms are present. Examples would be something like this. 5 iron oxide. So before we were talking about rust. So this would be a chemical formula, for example, for rust. So we have iron oxide. So notice that this 2 here says that we have 2 irons there, and we have 3 oxygens. But if we have a 5 in front of this coefficient, almost kind of like you're distributing in math, this 5 could distribute to both this iron and then also to the oxygen. So if you wanted to know how many iron atoms you have in 5 compounds of iron, or iron oxide, of rust, we would say 5 times 2, and so we would get 10 iron atoms, and 5 times 3 of the oxygen here would be 15 oxygen atoms. Okay, so we would have 10 iron and 15 oxygen, because we take this 5, the coefficient, and multiply it by these subscripts. So 5 times 2 is 10, and 5 times 3 is 15. A compound is just a pure substance that consists of 2 or more elements chemically combined in a fixed ratio. We've already kind of used that definition already. And then the chemical formula is just a combination of chemical symbols, coefficients, and subscripts that identify the element and number of atoms of each element in a compound. So this is when we bring it all together. Like before, when we had that 5Fe2O3, that was a chemical formula. So let's look at a couple of examples. H2O, right? So here we have 2 atoms of hydrogen, 1 of oxygen. We know that as water. NaOH, that's 1 sodium, 1 oxygen, and 1 hydrogen. And we know that because if there isn't a subscript here, it is assumed that it is a 1. Okay, so this is like as if you had 1s on each of these, right? If there isn't a number there, it's assumed that it's 1. Another example, calcium. So here's CaHCO3. So notice here we have one calcium atom, right? Because there's just this one calcium here. There's a 1 right here. But let's think about this guy inside of the parentheses. So note these parentheses come around like this, and then we have this subscript of 2 on the outside of all of that. Well, these subscripts get distributed into every single one of these elements that is there. So this 2 comes in here, and since we have 1 hydrogen here otherwise and 1 carbon, well, we multiply this 2 times both of those numbers. So when we do that, we have 2 times 1, and we get 2 HCO3 groups, which means we have 2 hydrogen atoms, 2 carbon atoms, and how many oxygens? If there's already 3 here, and we have a 2 outside of that, right? We have to multiply those together. 3 times 2 is 6. Yeah, 6 oxygen atoms. What about this one? This is magnesium phosphate. So Mg3PO4 2. So how many magnesiums do we have? How many of these? Well, you should be looking right here at this number. We have 3 of them, right? And then how many phosphate groups do we have? We're going to learn how to name these later on, but this is called a phosphate, this whole thing. Well, we have 2 of them. We have 2 phosphate groups, 2 PO4 groups. So that means inside of one PO4 group, we have 1 P and 4 O's, right? But we have 2 of those groups. So we just need to make, for phosphorus, we need 2 of them. And for oxygen, if it's O4 in each group and we have 2 groups, if there's 4 oxygen in every group and we have 2 groups, we have 1 group plus a second group. So 4 plus 4 is 8. Yeah, so 2 times 4 is 8. So 8 oxygen atoms. How many atoms of each element are present in each of the following formulas? Okay, what do you think for this one? For Na2S2O3. So how much sodium? How much sulfur? How much oxygen? You should have said 2 sodium, 2 sulfur, and 3 oxygen. That was kind of easy. What about the next one? Magnesium nitrate. MgNO3. In the NO3 group, there's 2 of those. So we're going to have 1 magnesium, right? How many nitrogen? 2. And how many oxygen? 6. Very good. What about this? 3CaBr2. So notice here we have a 3 on the outside here, a coefficient. I told you before, that gets distributed into everything, right? So we would normally just have a 1 here, but now we have a 3 outside. So it's 3 times 1. So how many calcium do we have? That's right, 3. And then how many bromines do we have? If we have 2 here normally, but we have a 3 outside, remember we have to multiply that by that subscript. So 3 times 2 is 6. Very good. So 3 calcium, 6 bromine. All right, this brings us to section 2B in your book on energy and matter. So let's talk about work and energy for a minute. So work is done anytime an object moves while a force is applied along its direction of motion. Note here, work only happens if the object moves in the direction of the force being applied. So the object has to be moving in the direction, along the direction of motion in which force is being applied. Otherwise, no work is being done. All right, so you can apply a force, but no work is done until it actually moves. Now, energy is the ability to do work. Now, work and energy are both measured in joules, is the dimensional unit that's used to measure both work and energy. Work is something that you do. Energy is something that you have. So energy is the ability to do work. Work is the actual enactment of that work. So I have a little picture here. You see this in your book as well. Can you identify different forms of energy in this picture? So we would have a nice class discussion about that. But since you're not all here and I can't talk to you about it, let's kind of look at this picture a little bit. What are some forms of energy that you see here? Well, you might see here this battery, for example, right? You see this battery down here. So inside of the battery, there are chemicals, right? So there's chemical energy inside of this battery. Now, these wires that are connected to it, and going down over here to this generator right here, right? In order for this energy to be transmitted over these electrical wires, we know that has to be an electrical energy, right? And so we have electrical energy that's pictured here. We also have, for example, notice here that we have wind that is blowing here, and we have a windmill that is being turned by that, which is then in turn turning these electrical wires that are inside of this generator, and it's generating electricity. So we have some mechanical energy that's going on here by the turning of those fan blades. We also, what kind of energy do we have here pictured with the sun? Well, as it's heating up the earth, we have thermal energy, right? Electromagnetic energy in the rays of light as well. But also inside the sun itself, we have nuclear energy going on, where hydrogen is coming together with hydrogen and fusing and making helium. And that fusion reaction is producing lots and lots of heat and energy being distributed. So mechanical energy is the sum of an object's kinetic and potential energies. You probably talked about kinetic and potential energies before in probably another introductory science class. Kinetic energy is the energy of motion. Potential energy is the energy of position. So often these are kind of depicted like as if you had a hill or something of that nature. Let's see here. If you had a hill or something like that nature like this, and you had a ball that was sitting at the top of the hill. So when it's up here, it has a lot of potential energy because its position is high. But if it's still right at that moment, it has zero kinetic energy. But the moment that the ball starts rolling down the hill, it starts losing potential energy because it's moving downward. But as it's moving downward, it's picking up speed, which means it's gaining kinetic energy. And if we got down here to the bottom of our hill, let's say it flattened out here, we'd have maximum kinetic energy, energy of motion, but minimum potential energy because it'll have fallen in position from up there down there. So mechanical energy is the sum of both kinetic and potential energies. So kinetic energy is the energy of motion. Potential energy is energy of position or condition. We said thermal energy in the previous slide, which is the sum of kinetic energies of all the particles within a substance. Acoustic energy is another one we didn't talk about on the previous slide, but this is energy that is carried in sound. There's also electromagnetic energy, which is energy carried in electromagnetic waves produced by vibration of charged particles that disrupts the electromagnetic field. Electrical energy, the potential energy of a charged particle through its position due to its position in an electrical field. And chemical energy, the potential energy stored in chemical substances. And then last but not least, nuclear energy, which is the potential energy that's found in the nucleus of an atom. Okay, so for our purposes in this class, we're going to be talking a lot about chemical energy and a little bit about electromagnetic energy, but mainly thermal energy and chemical energy will be the main ones we're talking about here. In physics, you'll talk more about electromagnetic and electrical energy, and then specialized sciences get into nuclear and that kind of thing. Because at the very end of the year, we'll talk about nuclear energy a little bit. So thermodynamics is a study of movement and conversion of energy, especially thermal energy. So I was going to give you guys a demonstration of this in class, but I'll just kind of explain what I would have done. I would have asked you, what's the difference between heat and temperature? And then ask you this question: which has more heat, a lit match or an iceberg? Now, that question is posed on purpose to kind of make you kind of think, well, wouldn't obviously a match have more heat than an iceberg? I mean, Iceberg would be seemingly cold to us, whereas a match, I mean, that's hot, right? So wouldn't the match have more heat? But a good way to kind of check this is if you were to take the match and to light it and then put it underneath the bottom of an iceberg, how much of the iceberg would melt as a result of the match? Yeah, not very much, right? And the thing is that we often confuse the ideas between temperature and heat. And the way I could demonstrate this is if I had a boiling cup of water right here in front of me, and I was to take an eyedropper and take out a drop of water from that, and then put out my hand and drop the drop of boiling water onto the top of my hand, and what would happen? Well, we'd be like, well, you probably feel the heat of that, right? But one drop of water is really not going to cause me much harm. And the reason why is that while the temperature of that one drop of water is the same temperature as the beaker or the cup full of water, it really doesn't have much heat, because heat is the summation of all of the energy, kinetic energy, found in the particles of the substance. But if I only have one drop of water, I don't have a lot of particles. But on the other hand, if I was to take that cold cup or that beaker and pour it over my hand, I'd be left with a really, really bad burn. And that's because while the temperature is always just a measure of the average kinetic energy, but heat is a measurement of the total amount of kinetic energy within a substance. So one drop of boiling water won't hurt you, but a cup of boiling water will definitely hurt you. Again, don't try this at home. I didn't tell you to go try this, but I just want you to understand that one drop of boiling water doesn't have much heat. And one match also doesn't have much heat. There's far more heat in an iceberg than a match. Far more heat. Again, because even though an iceberg looks cold to us and we don't think of it as being hot, it is hot in comparison with absolute zero. Absolute zero would be the point at which there is absolutely, it's a theoretical concept, but at the point at which there is no heat whatsoever. And we'll talk more about that in a minute. So heat is the movement of thermal energy due to temperature difference, and it always flows from warm to cold. Temperature always is flowing from hot substance to the cooler substance. That's the direction of thermal energy movement. Temperature, as I said, is the measurement of the average kinetic energy of all particles within the substance. Heat would be the measurement of the total amount of energy. Temperature is an average of that kinetic energy. So I can take that whole pot and get the same temperature as if I was to take out an eyedropper and measure that. If I took it out right away and took the measurement right away, I'd find that the little sample I got was the same temperature as the other, but the amount of heat in the little dropper is much smaller than the heat that's within the pot. So let's talk about the three laws of thermodynamics. The first law of thermodynamics is that matter and energy cannot be created or destroyed, but can change from one form to another. So matter and energy are neither created nor destroyed. This is the first law of thermodynamics, which, by the way, is a real problem for naturalists who don't believe that there is a God, because the big question that we can pose to them is, well, then how did we all get here? What started all of this? If matter and energy cannot be created or destroyed, but only change from one form to another, then there is no natural process by which you can explain the origin of everything. For us as Christians, the answer is easy. Creation is a miracle. It's an act of the holy, sovereign God. And because of his creative power and work, matter came into existence. In the beginning, God created the heavens and the earth. And that was a miraculous, supernatural event. This law is also referred to as the law of conservation of mass energy and is related to the law of energy conservation. So matter and energy can neither be created nor destroyed, just changing from one form to another. Matter and energy are always conserved. The total produced always equals the total consumed. The second law of thermodynamics is that the entropy of an isolated system will always increase. Entropy is a fancy word for disorder or randomness or dispersal. And it describes the fact that whenever you have an isolated system, entropy always increases. Things are always spreading out. You can cause something to be more greatly ordered, but in order to do that, you have to put energy in, and the net result will be further disorder in other places. So in order to organize one spot, there has to be disorder or energy put in, and disorder expands everywhere else. Again, a problem for naturalists who want to argue that things like exploded and became more ordered or more organized. What we see in science is things do not become more ordered or more organized without A, energy being implied, and B, intelligent design, like intelligence, creative organization in order to make that happen. Both, again, questions that naturalists or atheists, cannot answer, or their answers are just very, very poor, is what we can also say. All natural processes tend toward increased entropy and decreased usable energy. Entropy is a capital S, is the way we describe it, and we'll be talking about entropy later in our course. It's a mathematical measure of the dispersal of energy in a system. So here, a cup of coffee transfers thermal energy to the environment. The energy spreads throughout the room and becomes less usable, right? So while it's contained within the coffee cup, it's a nice warm cup of coffee, right? But left out for a while, eventually that heat will distribute itself out into the air surrounding it and become less and less usable to either you drinking the water or anyone else, or the coffee. The entropy of the universe is continuously increasing. Entropy is always increasing in the universe. The third law of thermodynamics is that we can never decrease a system's entropy to an absolute minimum. It's impossible to reach absolute zero. And by the way, the absolute zero that we were talking about in the previous slide is, again, a theoretical concept, and we'll talk about temperature scales in just a few minutes. So a system is everything within a set of boundaries defined by a scientist that is being studied. A system can be pretty much anything that you define it to be. It could be a beaker or a burner on a stove. That could be your system. You could be saying that the system is a rocket engine that you're looking at, or it could be a volume of air within the atmosphere. Any decrease in entropy in one part of the universe comes at the expense of increased entropy elsewhere. So if you want to decrease entropy here, it's going to come at the expense of increased entropy somewhere else. So the particle model of matter says that all matter is composed of tiny particles, atoms, molecules, or ions that are in constant motion. So the idea is that all of matter is actually always in motion. There's always a kinetic energy to all particles. Because remember, by the third law of thermodynamics, you can't get to absolute zero. So all particles in the universe are constantly in motion. It might be just like slight vibrations that we cannot even perceive with the human eye, but they're in constant motion. And this constant motion of fluid particles in random directions is due to their kinetic energy, or called Brownian motion. This was observed by Robert Brown in 1827. He described both translational motion, which is motion in straight lines, vibrational motion, which is small random vibrations, and rotational motion, which is spinning motion. Again, you don't need to necessarily remember all of those types of motion, but just understand that particles are continually in motion. Kinetic energy is the energy due to the motion of an object. The total kinetic energy is the sum of all of the types of particle motions within a thing. So whenever you're taking a temperature, you're taking the average of the kinetic energy. Remember, the total kinetic energy is also a description of the thermal energy that is present. The kinetic energy of a system is proportional to the mass of the system and the square of its velocity. This formula you've maybe seen before. It's more important in physics than it is in our class, but kinetic energy equals 1/2 mv squared. So the kinetic energy of a system is proportional to the mass times the square of the velocity, and then we divide that by 2. Again, that's a really important concept in physics, not so much something we're going to be dealing with a lot here in chemistry. All right. So in thermodynamics, we're typically interested in the movement of thermal energy. And there's 2 different words that we use to describe the movement of energy. One is called exothermic. Exothermic means that the energy is moving outward. It's exiting. It's releasing energy more than it is absorbing energy. And the other type of thermal reaction is an endothermic reaction, where the process absorbs more energy than it releases. I think the best examples of both of these is if you've ever had, like, for example, when it gets colder outside, you get one of those like warm hands things. They're like little pouches. You kind of like punch them, and then they start warming up because there's a chemical process inside of there where it's an exothermic process and it's letting off heat. There's also chemical cold packs, right? If you get hurt or something, sometimes some first aid kits will have a kit like that where you usually punch it or pop it in some way, and then it starts getting cold. That's an endothermic process where it's absorbing heat from its surroundings, and you put those like on wherever you're hurt. So both hot packs and cold packs are examples of both endothermic and exothermic reactions. So I'm sure that you guys are familiar with some temperature scales. Celsius is the one that's normally appealed to in a lot of our science classes, right? It's convenient for us because the scale is set where the boiling point of 100 degrees Celsius is the boiling point of water, and the freezing point of water is the 0 spot. So 0 degrees Celsius is freezing point of water, at atmospheric pressure, at sea level. Kelvin, on the Kelvin scale, an absolute temperature scale with 100 kelvins between boiling and freezing, but the boiling point of water on Kelvin scale is 373.15 Kelvin. The freezing point is 273.15 Kelvin, which tells you how cold is absolute zero. So on the Celsius scale, absolute zero is negative 273.15 degrees Celsius. But on Kelvin scale, it would just be 0 Kelvin. So the 0 on the Kelvin scale is absolute zero, which again, I told you is a theoretical concept. No one's actually ever gotten to that temperature. And if you're curious why that is, remember what I told you earlier about how heat transfers? It always goes from a place of higher heat to lower heat. So heat needs, in order to get colder, it has to move from a place of higher heat to a place of lower heat. The issue is when you're trying to get to absolute zero, in order to take away that last residual heat, you have to evacuate it to a space that's less than absolute zero. But absolute zero is absolute zero. You can't get any colder than that. And for that reason, you can get very, very close to absolute zero in specialized labs, but they've never actually been able to achieve absolute zero or the complete cessation of atomic activity. Now, whenever you're converting from Celsius to Kelvin, it's actually a pretty easy thing. If you have a temperature in Celsius, all you do is you add 273.15 and you'll have it in Kelvin. By the way, you never write degree Kelvin. You always write just Kelvin. So you will just write K. If you're writing degrees Celsius, you write the degree C. But in Kelvin, we just write K, not degree K. If you're converting from Kelvin to Celsius the other direction, well, think about this formula. You would just have to subtract this to the other side, right? So the temperature in Celsius is the temperature in Kelvins minus 273.15. So that's really convenient. The conversion from Celsius to Kelvin is a very easy one to do. What's not as easy is the Fahrenheit to Celsius or Celsius to Fahrenheit. These formulas are also still not all that difficult. To go from Fahrenheit to Celsius, you take the Fahrenheit measurement and you subtract 32 from it, and then multiply it by 5 and divide it by 9. And again, you can solve this equation in the other direction. So let's try this. While performing an experiment, you collected a sample of gas in a bottle immersed in 32.15 degrees of water, Celsius of water. What's the temperature in kelvins? We're going from Celsius to Kelvin. That's pretty easy. Right, what do I know? The temperature in kelvins or Celsius was 32.15 or 0.5. The temperature in Kelvin is what we're trying to figure out. The formula that we use is the temperature in Celsius plus 273.15. So we plug in our values. Our 32.5 plus 273.15, and we get 305.65 Kelvin. How about the temperature of seawater jetting from a smoker in the bottom of the ocean at Mid-Atlantic Ridge is 671.5 Kelvin. What is the temperature in degrees Celsius and Fahrenheit? So the Celsius is an easy one. Okay, so we write what we know. We know the temperature in kelvins was 671.5. We're trying to find its temperature in Celsius. The formula that we know is the temperature in kelvins minus 273.15. So when we plug in our values, we get an answer of 398.35 degrees Celsius. What's nice about the Celsius Kelvin ones, we're just adding or subtracting 273.15. Now, if we want to go from Celsius to Fahrenheit, we need to use another formula. But the formula that we had so far was just from Fahrenheit to Celsius. So in order to do this, we need to solve this in the other direction. We need to solve this for our Fahrenheit. So in order to do that, we're going to take this guy. We're going to multiply both sides by its reciprocal. So if we multiply this side by 9/5 and this side by 9/5, note what happens. The 9 cancels the 9, and the 5 cancels the 5 on this side. And then we're left with 9/5 TC. Then we can just add this 32 to the other side. So it looks kind of like this. Those cancel. We're left with 9/5 TC equals TF minus 32. We add the 32 to both sides, which cancels the 32s on this right side. And we're left with a formula: temperature in Fahrenheit equals 9/5 the temperature in Celsius plus 32. So again, plugging in the values that we have at 398.35 for temperature in Celsius. We multiply that by 9. We divide by 5. Again, you can do these in any order, right? You can divide by 5 first and then multiply by 9, or vice versa. And then add 32 last. Remember your order of operations. I don't know if you guys remember ever seeing this before, but it's called PEMDAS. This is actually a helpful one. It tells you the order. So you always start with parentheses, then exponents, multiply and divide, add, subtract. So that's what that stands for. Parentheses, exponents, multiply, divide, add, subtract. PEMDAS. It's a good one to remember. So we do the multiplication and divide before we do this addition. And we get 749.03 degrees Fahrenheit. Okay, we mentioned that the unit of joule is the unit that's used for work, energy, and heat. These are a couple other definitions. The calorie is also another way of measuring heat. It's the amount of heat that's required to raise the temperature of 1 gram of water 1 degree Celsius. We're going to be talking about this more later. For our purposes right now, just know what the joule is. The reason why calories are just brought up here is because usually that's what you see on food packaging, right? How many calories some food has. This brings us to our last section, 2C, states of matter. So the kinetic molecular theory says that properties of matter can be explained by the interrelationships between the forces between particles and the particles' kinetic energy. If energy is added to particles, their motion increases. Forces between particles limit the motion of the particles. So the common states of matter are solid, liquid, and gas. A solid is a state of matter that's characterized by closely spaced particles vibrating in a fixed position. They have a very definite shape and volume, kind of like these bricks in this wall, right? Very definite shape and volume. They are difficult to compress. That's because the atoms that are there are already pretty much tightly packed together, so it's hard to press them together any more than they already are. Liquids, on the other hand, are a fluid state of matter characterized by closely spaced particles that can slide past each other. Think of kind of like popcorn in a dish or marbles in a bowl. They can roll past each other, and they kind of like take up the volume of whatever they're sitting in. So like this example, right? These volumes are, the liquid is just taking up the shape of the container that they're in. They are fluid, they can flow. They have a definite volume, but a changeable shape, right? The shape changes depending upon what container it's within. And they're difficult to compress. So just like solids, liquids also are hard to press together any more than they are. This property is really important when it comes to hydraulics, right? Hydraulics is the use of fluids in order to, for mechanical advantage. And again, that's more of a physics concept, but just know that liquids are hard to compress. Because again, they are packed closely together. They can roll over each other, which gives them that fluidity, which is different than a solid, but they are still closely packed together. Now, a gas is a fluid state of matter characterized by widely spaced out particles that interact only in momentary collisions, and they're also known therefore as vapor. They have a variable shape and volume. Their volume is limited by the container. They're easy to compress, right? With gases, you can compress them and expand. They kind of just take up the space of the container that they're in. And they have highly mobile particles with high speeds. So the particles are moving around fast. There's a lot of flexibility. They can kind of be compressed or they can spread out. Now, I wonder if you know this or not, but a lot of times in science books up to this point, you've been told there are just 3 states of matter. But here I want to introduce you to 3 other states of matter. So you know solid, liquid, gas. But here's 3 others. Plasma, Bose-Einstein condensate, and quark-gluon plasma. Now, plasma is a gas-like substance. It's formed at very high temperatures that consists of high-energy ions. There is more plasma in the universe than there is any other type of matter. Okay, this is what is primarily making up, stars and stuff like that. But so plasma, high-energy gas-like substance. Bose-Einstein condensate is that substance which, when you approach absolute zero, I told you can't get to absolute zero, but when you get close to it, scientists have discovered this property that the thing becomes like Bose-Einstein condensate. It's kind of like a super liquid. So it's weird. It's really, really cold, and you think it'd be more and more like a solid. But actually, when it gets that very cold, it almost becomes like they call it a super liquid. And then quark-gluon plasma is a super high energy state in which protons and neutrons are shredded to reveal the building blocks of matter. And so this is like super, super high energy plasma. So whenever you have a phase change, it's a transition from one state to another. And remember, this usually happens due to the change of thermal energy being transferred. But changes in phase are physical changes. Remember that this is not a chemical change. When water becomes ice, it's still water, right? It's just frozen form. It's solid form. And when water boils and becomes steam, becomes water vapor, it's still water. It's just in gas form. So these are just physical changes. So whenever a solid turns to liquid, we call that melting. Whenever a liquid turns into a gas, we call that vaporization. Whenever something goes straight from solid to gas without transitioning through liquid, we call that sublimation. Here we have a picture of some of those like air fresheners where it's a solid thing, but it just odorizes right into a gas. Another really good example of this is dry ice. Right? Dry ice sublimates. It's called dry ice because when you have the solid, it's carbon dioxide that's been made a solid. It goes right from solid to gas, leaving no liquid behind. And that's why they call it dry ice. That's called sublimation. When we move from a vapor to a liquid, that's called condensation. And often you see it, for example, on these window panes. We see this in Texas when we have our air conditioners on really strong and it's really humid outside. Sometimes you'll get condensation on the glass. But it can happen the other way too. If you have a warm inside and cold outside, sometimes the water will condense on the outside. You also see this in bathrooms, right? When you have a shower going and it's really hot and the glass is cooler, and so the water vapor in the air condenses onto the mirror in your bathroom. It's called condensation. Freezing is whenever we have a liquid that turns to a solid. And deposition is whenever you go from a gas straight to a solid. So here's an example of frost. We don't get a whole lot of that here in Texas. Every once in a while we'll get a little bit of that. Snow and hail is other examples of going right from water vapor to a solid state. So here's kind of a chart with all of these on it. So condensation is when we go from a gas to a liquid. Vaporization is liquid to gas. Freezing is liquid to solid. Melting is solid to liquid. Sublimation is solid to gas. And deposition is gas to solid. So you need to be familiar with those 6 different changes and states of matter. You can kind of go over these slides a few times if you need to. And I close with one last question. Would a change of state be characterized as a chemical change or a physical change? Yeah, I've repeated this now a couple times in this lecture. So when we change state, when we go from liquid to solid or solid to gas or any of the other combinations, it is not a chemical change. It is a physical change. And why? Because the substance changes form, but it is still chemically the same substance. Well, that finishes the lesson for this week. So I think we got that in just about an hour. Hopefully you're able to see this and walk through it. Hopefully it wasn't too boring. Hope this is helpful to you guys. At least you can fast forward and rewind too if you need to at all. But I'll post this up onto YouTube. Hopefully it's useful to you. If you guys have any questions, please do reach out to me. You have all of my contact information. God bless you guys. Stay safe, stay dry with the storm coming in. And I'll see you guys hopefully, Lord willing, next week. God bless you guys.